Go ahead.
Whatever you want. Okay, so my name is Kentera. You all probably know me. So I did my report on three-dimensional states of stress, and my report introduces stresses in a three-dimensional solid body. Some of the topics I'm going to be talking about today are definitions, that way we can all sort of be on the same page when we go through different topics. The 9 components of stress, stress visualization, normal stress distribution, average shear stress, and matrix representation of stresses. So, in this picture here, we have an arbitrary solid body here, and what we're doing is we're cutting it with a section plane. We have forces acting on this solid body, and then we cut it with this section plane. And in order to keep up with Newton's third law, we need these resultant forces or resultant loadings to keep it in a state of equilibrium. And so our goal from there becomes finding stresses at that point O right there. So what we have here are where we took this section. The section plane here is called the elemental area, or the delta O, as it says there. There's 4 different types of resultant loadings. There's the normal, the shear, the torsional moment or torque, and then the bending moment. So the 9 components of stresses we have to derive them. So basically what we're going to do is break it down a little bit by looking at it in respect to different axes. So for example, if we're looking at the x-axis first, what we're going to do is we're going to take the limit of the elemental area with respect to the ratio of internal force over elemental area, and by doing that we drive it down and we find our normal stresses in the x-axis, and also we need it with respect to the 2 other axes, so the shear stress in the x-axis with respect to the y-axis and the shear with respect to the z. And so we now have our normal, we have our 2 shears for the other 2 axes. So our additional 6 come from looking at the other 2 axes, the y-axis and the z-axis. We have the normal in the y, normal in the z, and the shear in both of those. And so what we're going to look at first is the stress visualizations. And so what we can do is we take those 9 components and we put them on our axes. So if we want to just stick with the right-hand rule and what we've been doing, we do z-axis up, and so we have our normal, which is acting perpendicular to our elemental area here. We have the shear in the x here and the shear in the y with respect to z, so tau zx, tau zy, and we have those stresses. What we can do is put those onto a stress cube here, and so this plane here, this plane here, and this plane here will be our positive stress components, and likewise the opposite ones will be our negative stress components. So this makes it so we can use the right-hand rule in all of the examples that we do. So normal stress distribution, what we have is we can break it down even farther, and we can look at a body that is acting completely, or that its center axis is about a certain axis. So for example, like if we're going to use this pen, basically, what we have is, if we orient it this way with our z-axis up again, we have the z-axis acting in the center of this object. So just like we did with the other solid body, we're going to cut this plane and then find the stresses at a certain point in that elemental area of the section there. And so we do some awesome math that you can see in my report, and we get this equation here. The sigma equals the P over A, P being the internal resultant force acting along that specific axis that we're looking at. So this can be used for bars, beams, stuff like that, where you have the axial force acting in that bar or beam. And then the A is the cross-sectional area of whatever your object might be. So what I have is an example, and there's opportunity for a prize. I was going to bring candy and throw it at you, but instead, well, I ate all the candy, first of all. So what we're going to do instead is, if you can solve this problem, so if you have this paper, you can take a picture of this problem, whatever you want. If you solve this problem, I owe you an Aspen coffee, and it can be at any point, during finals week, whatever you want. Just be like, Mediana, I want an Aspen coffee, go get me an Aspen coffee, and I'll get it for you. So our question here is the 80 kilogram lamp supported by 2 rods, A and B, or A, B, and B, C, sorry, right here and right here. This one is at a 60-degree angle with this little thing here, and this one here is 3, 4, 5 triangle there. So if AB, this one here, has a diameter of 10 millimeters, and BC has a diameter of 8 millimeters, determine the average normal stress in each rod. So you have time to solve that now. I'm going to move on. Okay, so now we move on to the average shear stress. So we're going to solve it the exact same way that we found the other two. For example, we take our bar, in this case pen, take a cross-sectional area, and we find the rest of the stresses at that point. But instead of taking our section plane or perpendicular to the axis that we're looking at, we're taking the parallel plane of the shape. Awesome math again in our report. When we get this equation here, tau equals V over A. So the average shear stress at that point is equal to the internal shear force excuse me, over the cross-sectional area once again. Again, if you're too slow to get that last example, I have another one. So if you get both of them right, you get 2 copies. Yeah, you. So here's the second example. The question is determine the average shear stress in the 20 millimeter diameter pin at A. So A is here. This is just a larger picture of what the pin looks like. And then the 30 millimeter diameter at pin B. So right here. That's support beam. So we're determining the average shear stress. And take a picture of that, write it down wherever you want. So now we look at the matrix representation of stresses. So if we have an object that it has, and we want to see what kind of stresses are acting on it in all three dimensions, so all 3 axes, we can put it into matrix form here. So in this 3D stress matrix, we need to line up the normal stresses along the diagonal here. So the XX, YY, and ZZ, the normals are going to act along there. Here we have the shear stresses, and you can see that these two are reciprocals of one another. So we have the shear reciprocity of this one here, the tau xy is equal to tau yx because of shear reciprocity. So we're going to set it up like that. So all the x's, y's, and z's there. You can also, it doesn't have to be finding stresses in all 3 dimensions. You can also find it in 2 dimensions. For example, using it on planes that only act in 2 dimensions. So like the piece of paper acting in the y and the x directions, you can find the stresses in both those directions on this specific plane. And you can do that also in matrix form with, again, normal here and the 2 shears reciprocals of one another on those there. So example of that. Apparently I don't have. Okay, so we'll just call that a preview for the example in my report. If you want to see an example using matrix representation, it'll be in my report under examples. Okay, so did anyone solve those 2 examples in that one copy? Nobody?
Already?
Yeah, already.
We're paying attention.
Oh, that's so nice. Okay. Well, okay, if you solve it, fine, come to me and give me the answer. First 2 get the copies. I was going to go over the solutions, but I won't, so awesome. Any questions regarding any of that?
What was the next slide?
It was the solutions, but if I give it to you, then...
Oh, okay. Questions?
Okay. Questions?
You did say you did some other examples in
I
your
did,
report.
yeah,
Okay.
in the report.
Okay.
I'm missing the slide apparently. Awesome. Thank you very much.